So today we are going to learn three things. Number one, countable set. Number two, which is called uncountable set. And number three, that is partially ordered set. And obviously, we'll introduce the concept of lattice. So first, we'll discuss what is a countable set. Also, we'll emphasize or we'll learn about cardinal numbers, basically infinite cardinal numbers. These infinite cardinal numbers lies at the very foundation of modern mathematics. It is a vital instrument in the day-to-day work of many mathematicians, and we shall make extensive use of this ourselves. This theory, um, which was created by German mathematician Cantor, you all know, I have also mentioned earlier. This theory, which was created by German mathematician Cantor, this theory has great aesthetic appeal, for it begins with ideas of extremely simplicity and develops through natural stages into an elaborate and beautiful structure of thought. In the course of our discussion, as we proceed, we shall answer questions which no one before Cantor's time thought of or thought to ask. And we shall ask a question which no one can answer to this day. So, our aim is very clear. We will discuss or we shall answer questions which no one before Cantor's time thought to ask, and we shall ask a question which no one can answer to this day. Without further ado, we can say the question is, what is cardinal number? We can say that cardinal numbers are those used in counting. So what is cardinal numbers? Cardinal numbers are those numbers or those which are used in counting, such as the positive integers. Basically, we can also say them as natural numbers. What are those natural numbers? Like 1, 2, 3, etc. These are all familiar to us, but there is much more to the story than this. The act of counting is undoubtedly one of the oldest of human activities. The act of counting. Men probably learned to count in a crude way at about the same time as they began to develop articulate speech. The earliest men who lived in communities and domesticated animals must have found it necessary to record the number of goats in the village herd by means of a pile of stones or some similar device. If the herd was counted in each night by removing one stone from the pile for each goat accounted for, then stones left over would have indicated strays, and herdsmen would have gone out to search for them. Okay, so this is a simple story, and from that time or period itself, the art of counting has been started. So names for numbers and symbols for them, like ours, 1, 2, 3, these things would have been superfluous. The simple and yet profound idea of a one-to-one correspondence between the stones and the goats would have fully met the necessity of the situation. In a manner of speaking, we ourselves use the infinite set n, which contains elements like 1, 2, 3, such that of all positive integers as a pile of stones. They are called, or you can take it as pile of stones thing. We carry this set around with us as a part of our intellectual equipments. Okay, so this thing is our intellectual equipments, or you can say this as pile of stones. We carry this set around with us as a part of our intellectual equipment. Whenever we want to count a set, what do we do? Say we have a stack of dollar bills, we start through the set n and tally of one bill against each positive integer as we come to it. The last number we reach corresponding to the last bill is what we call the number of bills in the stack. If this last number happens to be 10, that you can say 10, then 10 is our symbol for the number of bills in the stack, as it also is for the number of fingers and for the number of our toes and for the number of elements in any set which can be put into one-to-one correspondence with the finite set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this set. So our procedure is slightly more sophisticated than that of our primitive savage. We have the symbols 1, 2, 3 like that. For the numbers which arises in counting, we can record them for future use and communicate them to other people and manipulate them by some operations of arithmetic. But the underlying idea, that of the one-to-one correspondence, remains the same for us as it probably was for him. The positive integers are adequate for the purpose of counting any non-empty finite set. Positive integers are adequate for the purpose of counting any non-empty finite set. And since outside of mathematics all sets appear to be of this kind, they suffice for all non-mathematical counting. But in this world of mathematics, we are obliged to consider many infinite sets, such as the set of all positive integers itself, or the set of all integers, or you can say the set of all rational numbers, real numbers, or the set of all points in a plane, and so on. So it is often important to be able to count such sets. And it was Cantor's idea. To do this and to develop a theory of infinite cardinal numbers by means of one-to-one correspondence. In comparing the sizes of two sets, the basic concept is that of numerical equivalence as defined in the, or you can easily get that from our previous talk, what is meant by numerical equivalence. So this basic concept of numerical equivalence, it can be, you can avail from the earlier talks. We recall, or for this today's purpose, we recall that two non-empty sets we have two non-empty sets X, capital X and capital Y. They are said to be numerically equivalent if two sets X and Y are said to be numerically equivalent if there exists a one-to-one mapping of one onto the other, or and this amount to the same thing if there can be found a one-to-one correspondence between them. So I am again repeating, two non-empty sets X and Y are numerically equivalent if there exists a one-to-one onto mapping, one-to-one onto mapping between these two sets, or you can say there exists a one-to-one correspondence between them. Now, to say that two non-empty finite sets are numerically equivalent is of course to say that they have the same number of elements in the ordinary sense. Two non-empty finite sets are numerically equivalent is of course to say that they have same number of elements in the ordinary sense. So if we count one of them, we simply establish a one-to-one correspondence between its elements and a set of positive integer of the form 1 to up to n. And then we say that n is the small n is the number of elements possessed by both or the cardinal number of both. Okay. The positive integer are the finite cardinal numbers. We encounter many surprises as we follow Cantor and consider some numerical equivalence for infinite sets. The set capital N, which is equal to set containing 1, 2, 3, this all positive integers. It is obviously larger than the set containing the even integers, such that 2, 4, 6, this set, because it contains this set as a proper subset. It is obvious. It appears on the surface that capital N has more elements, but it is very important to avoid jumping to conclusion when dealing with infinite sets, and we must remember that our criteria in these matters is whether there exists a one-to-one correspondence between the sets, not whether one set is or is not a proper subset of other. Will not mean that. As a matter of fact, the pairing, if we pair the elements of these two sets such that one is paired to 2, 2 is paired to 4, 3 is paired to 6, 4 is paired to 8. In this way, n is paired to 2n. This pairing serves to establish a one-to-one correspondence between these two sets, in which each positive integer in the upper row is matched with the even positive integer directly below it, and these two sets must therefore be regarded as having the same number of elements. So it's very surprising, and we are able to establish a one-to-one correspondence between these two sets. These are very remarkable circumstances, for it seems to contradict our intuition, and yet it is based only on solid common sense. Now we shall see coming discussion that every infinite set is numerically equivalent to a proper subset of itself. Every infinite set is numerically equivalent to a proper subset of itself. Since this property is clearly not possessed by any finite set, some writers, or you can see many books, they use it as the definition of infinite set. In much the same way, like what we have previously discussed about the one-to-one correspondence between the set capital N with the set containing the even integers, in the same way, we can also show that the set N is numerically equivalent to the set of all even integers, where we have mapped 1 to 0, 2 is mapped to 2, 3 is mapped to -2, 4 is mapped to 4, 5 is mapped to -4, 6 is mapped to 6, 7 is mapped to -6, in this way. So we have established a one-to-one correspondence between the set N and the set of all even integers. Previously it was positive even integers, and now we are taking the set of all even integers, including the negatives one. Here our device is to start with 0 and follow each even positive integer as we come to it by its negative. Now in the same sense, the set capital N is numerically equivalent to the set of all integers. You can see that 1 is mapped to 0, 2 is mapped to 1, 3 is mapped to -1, 4 is mapped to 2, 5 is mapped to -2, in this way. It is of considerable historical interest to note that Galileo observed in the early 17th century that there are precisely as many perfect squares. What do we mean by perfect squares? That is those integers like 1, 4, 9, 16, 25. 1 comes from 1 square, 4 comes from 2 square, 9 comes from 3 square. That is which are numbers which are perfect squares. The Galileo observed that there are precisely as many perfect squares among the positive integers as there are positive integers altogether. This is clear form of pairing: 1 to 1 square, 2 to 2 square, 3 with 3 square, 4 with 4 square, 5 with 5 square. In this way, it struck him as very strange that this should be true, considering how sparsely strewn the squares are among all the positive integers. But the time appears not to have been ripe for the exploration of this phenomena, or perhaps he had other things on his mind. In any case, he did not follow up his ideas. So these examples should make it clear that all that is really necessary in showing that an infinite set X is numerically equivalent to N, capital N, is that we should be able to list the elements of X with the first, second, third, fourth, and so on. It should be done in such a way that it is completely exhausted by this counting of its elements. It is for this reason that any infinite set which is numerically equivalent to n is said to be countably infinite. Any infinite set which is numerically equivalent to n is said to be countably infinite. We say that a set is countable if it is non-empty and finite, or if it is countably infinite. So countable has two meanings. Number one, it may be finite and it may be countably infinite. One of the Cantor's earliest discoveries in his study of infinite sets was the set of all positive rational numbers. It was Cantor's earliest discoveries. So what is rational numbers? Actually, this set is very large. It contains n, that is the set of all integers or natural numbers, and great many other numbers, and also is actually countable. We cannot list the positive rational numbers in order of size. This thing we have done for positive numbers, beginning with the smallest, then the next smallest, and so on. But you can't do it here because there is no smallest element, and between any two there are infinitely many others. So we must find some other ways of counting these numbers, these rational numbers. Following Cantor, we can arrange them not in order of size, but actually we can arrange them according to the size of the sum of numerator and denominators. So you take sum of numerator and denominator. We can begin with all positive rationals whose numerator and denominator add up to 2. So there is only one possibility, and that is 1 by 1 is equal to 1. Next, we list with increasing numerator all those rational numbers for which the sum is 3. What can the numbers can be? 1 by 2 or 2 by 1. So there are 2 numbers. Next, all those which have the sum 4. So what are those numbers? 1/3, that is 1 by 3, or 2 by 2. Also 3 by 1. Now all those for which the sum is 5, these are like 1 by 4, 2 by 3, 3 by 2, and 4 by 1. In this way, all those numbers for which the sum is 6 are like 1 by 5, 2 by 4, 3 by 3, 4 by 2, and 5 by 1. And in this way. So we write these numbers according to increasing numerator. So obviously for a particular constant sum of numerator and denominator. So now if we now list all these together from the beginning and omitting those already listed, when we come to them, we get a sequence 1 half, 1 by 2, 2, 1 by 3, 3, 1 by 4, 2 by 3, 3 by 2, 4, 1 by 5, 5, in this way. This contains each positive rational number once and only once. So if we look at the figure, it gives a schematic representation of this manner of listing the positive rationals. In the figure, the first row contains all positive rationals with numerator 1. The second, all rational numbers with numerator 2, in this way. And the first column contains all with denominator 1. The second column, all with denominator 2. Third with denominator 3, in this way. Our listing amounts to traversing this array of numbers as the arrows indicate. You can clearly see the arrows from the figure, where of course all those numbers already encountered are left out. So we have shown a way to count the positive rational numbers. Positive rational numbers are countable. So now it is your task to show that the set of all rationals are countable. You can do it yourself. It's a very easy task. You yourself try the all rational numbers are countable. You can take help from the way we have proved that positive rational numbers are countable. You can extend this idea and do this task yourself. So it's high time that we christen the infinite cardinal numbers we have been discussing, and for this purpose we use the first letter of the Hebrew alphabet, Aleph, with 0 as a subscript. We say that Aleph naught is the number of elements in any countably infinite set. Okay. So repeat again that we use the first letter of Hebrew alphabet, Aleph, with 0 as a subscript, and we call it as Aleph naught. So Aleph naught is the number of elements in any countably infinite set. So our complete list of cardinal numbers, what we have taught, is 1, 2, 3, is up to Aleph naught. So we will expand this list. At this moment, we have this list. We have the list of cardinal numbers 1, 2, 3 up to Aleph naught. We will expand this list in the next slides. For now, suppose that M and N are two cardinal numbers. We have two cardinal numbers m and n, finite or infinite. The statement that m is less than n, which is obviously written as m less n, is defined to mean that if x and y are two sets with m and n elements respectively, the set x has m elements and the set y has n elements, then number one, there exists a one-to-one mapping of x into y. Number one, I repeat again that there exists a one-to-one mapping of x into y. Number two, there does not exist a one-to-one mapping of x onto y. So we have two cardinal numbers m and n. We say m less than n in this way, that if we have two sets x and y with elements m and n respectively, then number one, there exists a one-to-one mapping of x into y, and number two, there does not exist a one-to-one mapping of x onto y. Using this concept, it is easy to relate that our cardinal numbers, we can relate our cardinal numbers to one another or to other by means of the relation that 1 less than 2, less 3, less 4, up to less aleph naught. With respect to finite cardinal numbers, this ordering corresponds to their usual ordering as real numbers. Until now, we have discussed what we mean by countable sets, and we also discussed the concept of cardinality for countable sets. Now we move on to uncountable sets. We move to uncountable sets, and we are going to discuss the cardinality, the sense of cardinality in this regards. So all the infinite sets we have considered in the previous section were countable. So it might appear at this stage that every infinite set is countable. You can think of, if this were true, if the end result of the analysis of infinite sets were that they are all numerically equivalent to one another, then Cantor's theory would be relatively trivial if this were true. But this is not the case, because Cantor himself discovered that the infinite set R of all real numbers, the set R of all real numbers, is not countable. Or we may say it otherwise, that R is uncountable or uncountably infinite. So every infinite set is not countable. There are sets, in fact, is very trivial, or we are used to the set of all real number, is also very interesting that this set of real number R is uncountable or uncountably infinite. Since we customarily identify the elements of R with the points of real line, this amounts to the assertion that the set of all points on the real line represents a higher type of infinity than that of only the integral points or only the rational points. It's a higher type of infinity. Cantor's proof of this is very ingenious, but it is actually quite simple. In outline, the procedure is as follows. We assume that all the real numbers can be listed. So we will do the proof in a strange way. We firstly take that the set of all real numbers can be listed, and in fact have been listed. Now we produce a real number which cannot be in this list, thus contradicting our initial assumption that a complete listing is possible. So the structure of proof goes in this way. Now, how do we do this thing? First of all, we have to represent a real number. In representing a real number by decimals, we use the scheme of decimal expansion, in which infinite chains of 9s are avoided. For instance, we can write half as 0.5000 in this way and not as 0.4999 this way. In this way, we can guarantee that each real number has one and only one decimal representation. Suppose now that we can list all the real numbers and that they have been listed in a column, like you can see a list I have already written where we use a particular number, these numbers for the purpose of illustrations only. So it's like that. We have listed 3 numbers. You can see in this way. We have separated out that integral parts and decimal parts. Since it is impossible actually to write down the infinite list of decimals, our assumption that all the real numbers can be listed in this way means that we assume that we have available some general rule according to which the list is constructed. So, since it is impossible to actually write down this infinite set, we are taking some rule to list down these elements. A general rule. This rule, according to which this list is constructed, is similar to that used for listing the positive rationals. How? And that every conceivable real number occurs somewhere in this list. So how can we represent the real numbers? We demonstrate this assumption is false by exhibiting a decimal point A1, A2, A3 in this way, which is constructed in such a way that it is not in the list. We choose A1 to be 1 unless the first digit after the decimal point of the first number in our list is 1. So we choose A1 to be 1 unless the first digit after the decimal point of the first number in our list is 1. If it is 1, in that case we choose A1 to be 2. Clearly, our new decimal will differ from the first number in our list regardless of how we choose its remaining digits. It should be different. And now, how to choose A2? We choose A2 to be 1 unless the second digit after the decimal point of the second number in our list is 1. If it is 1, in that case, we choose A2 to be 2. Just as above, discussion or this list, our new decimal will necessarily differ from the second number in our list. We continue this building process or building up these decimals, point A1, A2, A3 in this way, and since the process can be obtained or can be continued indefinitely, it defines a real number, obviously real number in decimal form, which is different from each number in our list. So for our case, the numbers we have listed, for these numbers we can construct a number 0.121 in this way. These are for only illustrations purpose. According to the list what we have taken, we can construct a real number 0.121, which is obviously is not in the list. So this contradicts our assumption that we can list all the real numbers, and it obviously completes our proof of the fact that the set R of all real numbers is uncountable. We know that the set of all rational points on the real line is countable. In fact, it was your task to show that the set of all rational numbers are countable. And we have just proved that the set of all points on the real line is uncountable. So, the set of all rational numbers are countable, whereas the set of all points on real line is uncountable. So I conclude at once from these that the irrational points on real line must exist. In fact, it is very easy to see by means I can give you some task, you can do it, that the set of all irrational numbers are uncountably infinite. To vary slightly, a striking metaphor coined by E.T. Bell, that the rational numbers are spotted along the real line like stars against the black sky, and the dense blackness of the background is the firmament of the irrationals. So you may be familiar with a proof of the fact that the square root of 2 is irrational. This proof demonstrates the existence of irrational numbers by exhibiting a specimen. Our remark, on the other hand, do not show that this or that particular number is irrational. They merely show that such numbers must exist, and moreover must exist in overwhelming abundance. So if we think that the set of all points on the real line R is uncountable because R is infinitely long, then we can disillusion him or disillusion you, anyone, by the following argument. This argument shows that any open interval on R, no matter how short it may be, any open interval on R has precisely as many points as R itself. So it's very interesting. Any open interval on R, no matter how short it may be, it has precisely as many points as R itself. Let A and B be any two real numbers with A less than B, and consider the open interval AB. Now the figure you see, it shows how to establish a one-to-one correspondence between the points P of AB and the points P dash of R. We bend, how to do? We bend AB into a semicircle, and we rest this semicircle tangentially on the real line R as shown in the figure, and we link P and P dash by projecting from its center. If formulas are preferred over geometric reasoning of this kind, we can say that y equals to a plus b minus a of x is numerical equivalence between any real number belonging to the open interval 0, 1, and y obviously belongs to AB, and z equals to tan of pi into x minus half is another numerical equivalence between open interval 0, 1 and all of R. So it follows that the open interval AB and R are numerically equivalent to one another. So we are now in a position to show that any subset X of the real line R which contains an open interval I is numerically equivalent to R, no matter how complicated the structure of X may be. The proof of this fact is very simple, and it uses only the Schroeder-Bernstein theorem and our above result that I is numerically equivalent to R. The argument can be given in two sentences. Since x is numerically equivalent to itself, it is obviously numerically equivalent to a subset of R. And R is numerically equivalent to a subset of X, that is I. Now it is now a direct consequence of Schreier-Bernstein theorem that X and R are numerically equivalent to one another. So two arguments are: the first, X is numerically equivalent to itself, so it is obviously numerically equivalent to a subset of R. And two, R is numerically equivalent to a subset of X. What is that subset? That is, subset is I. So according to Schreier-Bernstein theorem, X and R are numerically equivalent to one another. We must point out that all numerical equivalences up to this point have been established by actually exhibiting one-to-one correspondence between the sets concerned. In the present situation, however, it's not feasible to do, for very little has been assumed about the specific nature of the set X. Without the help of the Schreier-Bernstein theorem, it would be very difficult to prove theorems of this type. To give another interesting application of the Schreier-Bernstein theorem, so it's a very interesting application. So for that thing, we first consider coordinate plane R2 and a subset X of R2. What is that subset X? X is defined as a collection of points xy, the ordered pair, where X lies between 0 less than equals to X less than 1 and 0 less equals to Y less 1. So the set X is defined in this way, and we show that this set is numerically equivalent to the closed open interval I. What is I? I is collection or pairs xy where X is such that 0 less than equals to X less 1 and Y equals to 0. This I forms the base of X. You can see from the figure that I forms the base of X. Now, I is numerically equivalent to a subset of X, namely I itself. Our conclusion will follows at once from the Schreier-Bernstein theorem if we can establish a one-to-one mapping of X into I. This we do how? Let xy be an arbitrary point of X. Each of the coordinate X and Y has a unique decimal expansion which does not end in an infinite chain of lines. We form another decimal Z from this by alternating their digits. For example, if we have X equals to 0.327 and Y equals to 0.614, we take Z is equals to 0.362174 in this way. We now identify Z Obviously this cannot end in infinite chain of 9s, and obviously we can identify z with a point of I. This gives a required one-to-one mapping of x into I and yields the somewhat startling result that there are no more points inside a square than there are on one of its side. So it's a very startling result that there are no more points inside the square than there are on one of its sides. We have introduced the symbol LF naught for the numbers of elements in any countable infinite set. We have previously introduced the symbol. At the beginning of our discussion, we proved that the set R of all real numbers is uncountably infinite. So we now introduce the symbol C. The symbol C, which is called the cardinal numbers of the continuum for the numbers of elements in R. C is the cardinal number of R and of any set which is numerically equivalent to R. Previously, we have demonstrated that C is the cardinal number of any open interval. How? We have demonstrated via some examples of numerical equivalence. From that, it follows that C is the cardinal number of any open interval or of any subset of R which contains an open interval and of the subset X of coordinate plane, which was again illustrated in the figure in the previous page, the second figure. So our list of cardinal numbers has now grown to 1, 2, 3, LF naught, and then C. So they are now related to each other by the relation 1 less than 2, less than 3, up to less than LF naught, and then LF naught is less than C. At this point, we encounter one of the most famous unsolved problems of mathematics. The question is there any cardinal number greater than LF naught and less than C? No one knows the answer of this question. So is there any cardinal number between LF naught and C? His answer is not known. Cantor himself thought that there is no such number, or in other words, C is the next infinite cardinal number greater than LF naught. And his guess has come to be known as Cantor's continuum hypothesis. So what is Cantor's continuum hypothesis? That there is no cardinal number between LF naught and C. This continuum hypothesis can also be expressed by the assertion that every uncountable set of real numbers has C as its cardinal number. So any uncountable set of real numbers has C as its cardinal number. There is another question which arises naturally at this stage, and this one we are fortunately able to answer. The question is, are there any infinite cardinal numbers greater than C? The answer is yes. There are. For example, the cardinal number of the class of all subsets of R. The example is the cardinal number of the class of all subsets of R. This answer depends on the following fact. If X is any non-empty set, then the cardinal number of X is less than the cardinal number of the class of all subsets of X. So X is any non-empty set, cardinal number of X is less than the cardinal number of the class of all subsets of X. So we prove this statement as follows. So before going to the proof, we again emphasize two questions. We have already said in the beginning of our lecture that we will come across the two very fundamental or important questions on the way. The question number one is the continuum hypothesis. The question is there any cardinal number which lies between F0 and C? Obviously the answer is not known. There is no proof. Cantor himself believed that there are no cardinal numbers, and this continuum hypothesis can also be expressed by the assertion that every uncountable set of real numbers has C as its cardinal number. And obviously the second question which we can answer, that is there any set or is there any cardinal number which is greater than C? And of course the answer in this case is yes. So how to give the example, or how to be sure that this is true? The answer depends on the following fact, that if X is any non-empty set, then the cardinal number of X is less than the cardinal number of all the class of all subsets of X. So we are going to the proof of this thing. So we prove the statement as follows. So in accordance with the definition which I have discussed previously in the previous slides, we must show that number one, there exists a one-to-one mapping of X into the class of all its subsets. There exists a one-to-one mapping of X into the class of all its subsets. And number two, that there does not exist such a mapping of X onto this class. So number one, there exists a one-to-one mapping of X into the class of all its subsets, and number two, there does not exist such a mapping of X onto this class. Now to prove number 1. To prove number 1, we have only 1.2, or we have only 1 point to see that the mapping from X to the set containing X. This makes correspond to each element X, that the set containing X, which consists of the element X alone. So we have pointed out a mapping. So what is that mapping? We map an element X to a set containing that element X alone. So we have shown a one-to-one correspondence between the set X into the class of all its subsets. Now we come to the proof of 2, and we will do this proof in a strange way, rather indirectly. For this proof, we assume, so what do we have to prove? We have to prove that there does not exist a mapping of X onto the class of all subsets of X. There does not exist any onto mapping, and we prove from the contradiction, and that is, we say, or we can assume, that there does exist a one-to-one mapping F of X onto the class of all its subset. So since we prove indirectly, we assume that there exists such a mapping. Now let capital A be the subset of X, which is defined as follows. A is collection of all X such that X does not belongs to F of X. Now this mapping we have assumed, the mapping F we have assumed it is onto mapping. So since the mapping is onto, there must exist an element small a in capital X such that F of A is equals to the set A. It's very obvious. We have defined the set A, which is the collection of all elements X, where X does not belongs to F of X and F is onto mapping, we have assumed. So since this mapping F is onto, there must exist an element A in capital X such that F of A is equals to A. Now, what is, or where is the element A? Where does it belong? There may be two cases. If A is in capital A, or A does not belongs to capital A. Firstly, we assume that if A is in capital A, if A is in capital A, then by the definition of capital A, the set capital A, we have A does not belongs to F of A. Now, since F of A is equals to A and A does not belongs to A, this is a contradiction. So A cannot belongs to A. So we have taken a set, or we have taken the set A. We again repeat that we take the set A as a set containing all elements X such that X does not belongs to F of X, where F is onto. Now, since our mapping F is onto, there must exist an element A in X such that if A is equals to the set E. This should be the case because the map F is from a set X to the class of all subsets of that set X. So, and F is onto, so there must exist an element A in X such that if A equals to capital A. Now, where is the element A? If A is in A, then by definition of A, we have A does not belongs to F of A, and since F of A is equals to capital A, obviously A is not, or A does not belongs to capital A. So this is a contradiction. So A cannot be or cannot belongs to the set A. But what if A is not an element of A? That is, A does not belongs to A. Then again, by the definition of A, we have A belongs to FA or A belongs to capital A, which is another contradiction. So if we take A is not in A, that means by the definition of A, we have A belongs to F of A or A belongs to capital A, since F of A equals to A, which is a contradiction. The situation is impossible, so our assumption that such a mapping exists must be false. So the result guarantees that given any cardinal number, there always exists a greater one. So if we start with a set x1 which contains the element 1, only one element, then there are two subsets, the empty set phi and the set containing 1 itself. There are two subsets. Now if x2 is set containing 1 and 2, then there are four elements, four subsets: phi, the set containing 1, the set containing 2, and the set containing 1 and 2. If x3 equals to a set containing 1, 2, and 3, containing 3 elements, then there are 8 subsets: phi, the set containing 1, set containing 2, set containing 3, the set containing 1, 2, 1, 3, 2, 3, and the last set containing 1, 2, 3, that is the set x3 itself. So in general, if xn is a set with n elements where n is any finite cardinal number, then xn has 2 to the power n subsets. So if we know, or if we now take n to be any infinite cardinal number, the above facts suggest that we define 2 to the power n to be the number of subsets of any set with n elements. If n is the first infinite cardinal number, that is LF naught, then it can be shown that 2 to the power LF naught is equals to C. The simplest proof of this fact depends on the ideas developed in the, or we will say develop here. So how to develop this idea? So firstly, we consider the closed open interval 0 1, where 0 is closed and 1 is open, and a real number x in this set. So our concern is with the meaning of the decimal, binary and ternary expansion of x. For the sake of clarity, let us take x to be 1/4. So how do we arrive at the decimal expansion of 1/4? First, we split the interval closed open interval 0 1 into 10 closed open intervals. 0 1 by 10, 1 by 10 to 2 by 10, and in this way 9 by 10 to 1. All intervals are closed open. Left hand side is closed and right hand side is open, and we use 10 digits 0 1 2 3 4 5 6 7 8 and 9 to number them in order. So our number 1/4 belongs to exactly one of these intervals. So we can see that 1/4 belongs to the interval 2 by 10, 3 by 10. It's very easy to see. So we have labeled this interval with the digit 2 as in the nomenclature. So 2 is the first digit after the decimal point in the decimal expansion of 1/4. So this is a way. So we can say 1/4 equals to 0.2 ... These things we will discover. So how to discover these things? We split the interval 2 by 10, 3 by 10 in 10 closed open intervals. 2 by 10 to 21 by 100, 21 by 100 to 22 by 100, in this way 10 closed open intervals, and we use 10 digits to number these intervals in order. So now our number 1/4 belongs to 25 by 100, 26 by 100, which is labeled with the digit 5. So 5 is the second number after the decimal point in the decimal expansion of 1/4. So 1/4 is equals to, until now we have 1/4 equals to 0.25 ... So we continue this process. Exactly as we started it, and we can obtain that decimal expansion of 1/4 to as many places as we wish. As a matter of fact, if we do continue, we get 0 at each stage from this point on, and ultimately 1/4 becomes 0.25000. This goes on. So we should we have noticed that there is no ambiguity in this system, as we have explained. Contrary to customary uses, 0.24999 is not to be regarded as another decimal expansion of 1/4, which is equivalent to 0.2500. So in this system, each real number x in the closed open interval 0 1 has one and only one decimal expansion, and this cannot end in an infinite chain of lines. There is nothing magical about the role of the number 10 in the above discussion. If at any stage we split our closed open interval into, you can say, 2 or 3, we can take 2 typical closed open intervals, and if we use 2 digits 0 and 1 to number them, we obtain the binary expansion of any real number x in 0 1. So you can check it's very easy to check. We can check that the binary expansion of 1/4 easily you can check as it will come as 0.01000 in this way. And similarly, the ternary expansion of x is found similarly. At each stage, we split our closed open intervals into 3 equal and closed open intervals, and we use the 3 digits 0, 1, and 2 to number these intervals. So you can thought a moment and you can convince yourself that this ternary expansion of 1 by 4 is 0.020202 in this way. Just as the decimal expansion of a number in 01 cannot end in an infinite chain of 9s, so also its binary expansion cannot end in an infinite chain of 1s, and its ternary expansion cannot end in an infinite chain of 2s. So we have developed an idea, a simplest idea, which we will use to prove that 2 to the power alpha naught is equals to c. This idea we will use in our next slides. So we will now use the machinery we have introduced in the previous slides to give a proof, or to show you a proof how to prove 2 to the power alpha naught is equals to c. So for this, consider two sets. Number one, set n, which is obviously the set containing 1, 2, 3 and these elements, and a set I, which is the closed open interval 0, 1, where 0 is closed and the side 1 is open. The first sets, the first of the two sets in this set n has cardinal number alpha naught is obvious. We have already proved it, discussed it, and the second set, this I, this has a cardinal number c. This is also very trivial, and we have discussed it is previously. So up to that it is clear. So now we denote n bar as the class of all subsets of n. And so now we denote by n bar a class of all subsets of n. Then by the definition of n bar, this set n bar has cardinal number 2 to the power alpha naught, because it's very simple. The set n has cardinal number alpha naught, so since n bar is the collection of all subsets of n, so it should have cardinality 2 to the power alpha naught. So our proof amounts to showing that there exists a one-to-one correspondence between n bar and I. So we begin by establishing a one-to-one correspondence or one-to-one mapping f of n bar into I. If A is a subset of n, then f of A is that real number x in I whose decimal expansion x equals to point d1, d2, d3 in this way is defined by the condition that dn is 3 or 5 according to as n is or is not in A. So if n is in A, dn is 3. If n does not belongs to A, then dn is 5. You can take any other two digits, it will work in the same way as long as neither of them is 9. Now we construct a one-to-one mapping G of I to n bar. If x is a real number in I and x is equals to point b1, b2, b3 in this way, is this binary expansion, so that each bn is either 0 or 1, then g of x is the subset A of n defined by is equals to collection of all n's such that bn equals to 1. So we conclude the proof with an appeal to the Schroeder-Bernstein theorem, which guarantees that under these conditions n bar and I are numerically equivalent to one another. So we have shown a function f that is one-to-one between n bar into I, and secondly we have constructed another function g, obviously, which is one-to-one and into function from I to n bar. So then we have used the Schroeder-Bernstein theorem, that is this condition 1 and 2 both implies, or you can, from this condition you can use Schroeder-Bernstein theorem, and this Schroeder-Bernstein theorem assures that n bar and I are numerically equivalent. Hence we have proved that 2 to the power alpha naught is equals to c. So it is a very interesting application of Schroeder-Bernstein theorem. So if we follow up the hints contained in the fact that 2 to the power alpha naught is equals to c, and we successively form 2 to the power c, 2 to the power 2 to the power c, and so on, we get a chain of cardinal numbers which are related in this way, that 1 less 2 less 3, in this way less lf naught, obviously lf naught is less c, and then c less 2 to the power c less 2 to the power 2 to the power c, in this way, in which there are infinitely many infinite cardinal numbers. There are infinitely many infinite cardinal numbers. So clearly there is only one kind of countable infinity, which is we can always say or symbolized by lf naught. This is countable infinite, and beyond this there is an infinite hierarchy of uncountable infinites or infinities, which are all distinct from one another. At this point we bring our discussions of the matters to close. We have barely touched the Cantor's theory and have left entirely to one side. For instance, all questions relating to the addition and multiplication of infinite cardinal numbers and the rules of arithmetic which apply to these operations. We have developed these ideas not for their own sake, but for the sake of their application in algebra and topology. And our main purpose throughout the last slides, to last more topics, has been to give you some of the necessary insight into countable and uncountable sets and the distinction between them. So here we finish our lectures, and at this moment I can give you a task or a problem which you can do it yourself. So the task is to prove that every infinite set is numerically equivalent to a proper subset of itself. So you will try to prove this task, and we end our discussions here. Thank you.